Okay, welcome back. So maybe we start with the opportunity for raising more questions about the PIV because the time was over in the first session. So are there any further questions remaining for PIV? Well, that seems not to be the case, such that we can now switch gears and continue now and going into spectroscopy, where I will focus on thermometry. Well, quite clearly you have seen that already in understanding combustion processes. Well, all of these sub-processes are influenced by the local gas temperature. Yeah? So chemical kinetics, for example, heavily depends on the local temperature based on the Arrhenius type kind of reactions underlying the chemical mechanisms. The viscosity, density are dependent on the local temperature, and thereby you have an influence via temperature on the transport properties. Phase change is dependent on temperature, of course, in terms of evaporation rates and so on. And so one of the most important quantities after having an idea about the flow field in my eyes is to have a good idea about local temperature measurements. And so that is shown here once again. Chemical kinetics, gas density, viscosity are influenced by the temperature, as well as, for example, the progress variable is built out of, or can be built out of the temperature, the local temperature in premixed combustion, and thereby as well you would have measuring the temperature a direct access to turbulence chemistry interaction. And so, well, you need ideally a technique that allows you to measure local temperatures accurately, meaning that you have no systematic error. Ideally, precisely, meaning that you have no or very small statistical error, which is very often coming through noise. And of course, you want to have it locally, ideally in the range of the Batchelor scales. The Batchelor scales are the equivalent to the Kolmogorov scales, but for scalars. In flows with a Schmidt number of 1, like in gaseous flows, the Kolmogorov and the Batchelor scales are almost equal, such that we can refer to the same estimation we have had in the previous session about the spatial dependency. However, meaning that if you want to resolve the Batchelor scales, ideally you want to have a resolution in the order of better than 50 microns, which is very difficult to achieve, if not impossible. All right. So we have then further to distinguish whether you're working on a laminar or in a turbulent flow. When you have a laminar flame, making a flame laminar is really easy. It's just determined by the Reynolds number. Making a laminar flame stationary is not so easy, because most of these laminar flames are very sensitive to any changes in the surrounding, meaning that you have to decouple any convection from your lab from your flame. And that is taking a huge effort to make a laminar flame really stationary. However, if you have both fulfilled, then you have no temporal variation. However, you typically have very strong gradients, for example, in the heat release zone, meaning that you have large spatial variations, such that the resolution requirements in time are none, which is good, in space high, depending on what you're looking at. Yeah? Of course, if you have higher pressures, like a laminar stationary flame, a Bunsen flame under 10 bar or 50 bar, there you have much steeper gradients than at low pressure. That's why very often people are looking in low pressure flames, because then you have less requirements in terms of spatial resolution. Okay. If you have interest in turbulent, statistically stationary combustion, of course you have, in addition, a temporal variation and still the spatial variation. And the requirements ideally are that you, in time and space, resolve time and length scales based on this estimation of Batchelor time and length scales. That can be, with a Schmidt number, can be calculated out of the Kolmogorov numbers, and if the Schmidt number is 1, then Batchelor and Kolmogorov, as I said, are equal. Well, of course, people have used very often non-intrusive sensing like thermocouples or resistant thermometers, but I would just briefly explain why this is not a good thing to do. The first is you have large systematic errors, because whenever you stick something like this into your flow, you have heat transfer, and then you have heat conduction. Then you have, of course, if this thing is heated, radiation losses. You have an obstacle in the flow, meaning that the flow is changed, and you might even have catalytic reactions. And referring to literature, even you have a steel surface, if you're above 400 Kelvin, then you have an influence of catalytic reactions, meaning that you're changing the flow. You can say that these sensors are not really sustainable because of the melting points. If you have a flame temperature maybe of 2200 Kelvin, you wouldn't have even any thermocouple working there. Type S thermocouples go up maybe up to 1900, 1950 or so, and even that, they wouldn't last for very long. So you have not even a chance to measure that. And even if you would do so, you would have to compensate somehow the radiation losses. You need a model for that. And this is not a good technique. If you need a model to correct your signal for the real temperature. Then you have typically extensions in the millimeter range. Let it be here a millimeter diameter. So you have no chance to resolve anything in space. And even in time, because of the response time, this is the time, this is the temperature, and assume that you have a rectangular time, a change of temperature in time. This is this green dotted line. If you have a second order system that can be assumed for this kind of thermocouples, for example, the response would be like that, and that can take many microseconds or even milliseconds, depending on the heat capacity of your intrusive sensor. And so resolving small fluctuations in the order of, let's say, a few microseconds would not be feasible with this kind of sensors. That's why I think it's not well suited. However, of course, it is very often used. Whenever you use it, you have to be aware of the limitations coming with that. And so mistrust absolute temperatures from thermocouples when you use it to compare your modeling, for example, to it. Doing non-intrusive diagnostics means you have to use spectroscopy. One possibility would be to use thermal radiation. Well, thermal radiation in gaseous flames is maybe not a good choice because what you see is, for example, the emission from CH or OH radicals. That means those radicals are electronically excited through the reaction, in the reaction zone. You would see then, for example, this bluish color over here, that it might come from CH star that emits at 430 nanometers and is produced in the flame front. It doesn't last very long, and in the post-flame region it is decomposed. However, whenever you have electronically excited molecules for temperatures around 2000 Kelvin, you can be sure they are not in equilibrium. Yeah? It's not in equilibrium. And that means whenever you get here something like a temperature based on the Boltzmann distribution, which we discuss later on out of that region, it would be not correct. You could think of thermal radiation. Well, thermal radiation could be used, for example, in sooty flames, and if you want to measure the particle temperature, people use the Planck's law to get that and assume a certain emissivity because it's not a perfectly black body radiation you get. Maybe you have to look out of the window and say the emissivity is 0.9 or 0.92, no one knows, which means it will not be accurate, but at least you can see, of course, trends, yeah, even if you're not accurate. The better way to do it is really probing spectroscopically, for example, the Boltzmann distribution, yeah, which means we have to go back to quantum mechanics to understand where the Boltzmann distribution comes from, or which is related to the Boltzmann distribution, but not purely. You exploit temperature-dependent absorption of larger molecules or temperature-dependent emission of larger molecules. That's why I'm writing bands. Yeah, these are not single lines from rotation lines, but for a multiple of rotation lines. I'll come to that in a second. Or the third alternative, you try to measure the density. Once you have the density, then you presume the validity of the equation of state, the ideal gas law, for example. If you have the density and you know the pressure, then you can relate it to the temperature. That's the third method. Okay, so those diagnostics in general, you can say, are well suited to many applications in combustion research, but as always in diagnostics, there is not the single best method. It really depends, again, on the purpose you're following. The disadvantage clearly is the effort is high, you need expert knowledge, and very often a large optical access. And that's why you wouldn't find that kind of temperature measurements very often in industry. Yeah, they do PIV nowadays very often, and spectroscopic techniques only for visualization of flames or things like that. Really measuring quantitative temperatures means not only factor 2 more effort compared to visualization, maybe it's a factor of 10 or so. Yeah. It is much more costly, and you need much more knowledge and experience about it. And that's why it is much less popular in industry, and we use it in academia primarily. Well, when we start now with a more detailed discussion, going back to what the alternatives are, the first I mentioned was the Boltzmann distribution. Is anyone in this room here aware of quantum mechanics? Have you heard that in your course of studies? No one? One person? Or a few persons? Okay, so for most of you, I guess you live in the world of the continuum, which is a great approximation, depending on the Knudsen number, but it is physically spoken wrong. Yeah? The world is not a continuum. The world is consisting of course, particulate matter, and this matter has the property of having non-continuous energies, internal energies. You're aware of the gas, let's say, seeing at single mass points without any internal structure. But if you go to molecules, they do have internal structures. And I will explain that in more detail, briefly only. But if you do so, then by quantum mechanics, you get 2 important numbers out. One is the internal energy values, and those are discrete. I guess most of you have heard about that. Discrete values, EI, and referring to them to a given, let's say, energy state, you have a degeneracy factor, because there might be different states giving rise to the same energy, but having different, let's say, internal properties, and those are summed up in this factor over here. So from solving the equations from quantum mechanics, you get this GI and this EI, yeah, for single molecules. If you now go to an ensemble and assume that you have thermal equilibrium, the charm of this equation is that you link these quantum mechanical properties, GI and EI, with a thermodynamic temperature, T. Yeah, this is thermodynamics, KT, and this is quantum mechanics. And this is given by this distribution function. For a given temperature, you find a certain fraction, this is called the Boltzmann fraction, a certain fraction of molecules which are in this specific energetic state EI, yeah, compared to the complete number of these molecules in this probe volume. And so if you would have access to measure this quantity Ni and know GI and EI, then you can, if this is your measurement, you can resolve the equation for T. And that is how we can trace back, or how you can combine a spectroscopic measurement with this, over this distribution function to this thermodynamic temperature. And if you do that, the advantage is that you do not have any calibration, because you trace your measurement back to a fundamental equation from statistical physics, which is true for a thermodynamic equilibrium. And only for those states we're interested, because only then you have a definition of the temperature. Well, you could use this equation principle as well to define the temperature instead of having a triple point of water like it's done in the SI units. The problem with this equation is that you very often you have to somehow get rid or know the absolute number of the molecules and this so-called partition function. This partition function looks easy because you have to calculate only the sum over all these possible states. But when you have a complicated molecule, and complicated already means 3-atom molecules, then you don't have the full information about that. So best possibility is maybe to look for ratios between Boltzmann fractions. And that is the way we will discuss it. The second opportunity I mentioned was to somehow measure temperature-dependent absorption or emission lines. And here I will discuss that later on in more detail. If you have a molecule like toluene that is very often used as a tracer, maybe in your gaseous flow, it is as well now as a vapor in your gaseous flow, then schematically this is shown here for normalized absorption bands, emission bands, sorry, where you see that with rising temperature, the emission band is shifting red. Yeah? So maybe this is at 300 Kelvin here, and maybe I don't know exactly the temperature here, maybe at 600 Kelvin, you find a different emission spectrum. And if you now measure either the whole spectrum or doing it with ratioing, as we'll discuss later, then you can link the spectroscopic properties with the temperature, but you need a calibration. And that is a drawback. Whenever you need to calibrate, that's not good. The third method that I mentioned was when you're able to measure a density, the number of molecules in your probe volume, then you can link that with the equation of state. Here's the simple ideal gas law, and if you know the pressure, then you can determine the temperature. Well, very often we know the pressure. If you have low Mach number flows, you might need only one pressure sensor somewhere, or you know it because you're possibly working in unconfined flames. Let's have a closer look now when we start the discussion about the Boltzmann distribution in more detail. We have to look a bit more into the degrees of freedom you have. I restrict myself to diatomic molecules, and some examples are shown over here. First of all, we presume that those atoms are bounded covalently, like in N2 or CO or NO. So this is what we're after. Then, yeah, well, we do have the degrees of freedom. In translation, we have 3 of them, okay? Because a molecule can move in this direction, and this direction, and this direction. That is clear. It does have, which is not shown here, because of these bounding, it has so-called molecular orbitals, and then the outer electrons, maybe the outest electron, which is called the valence electron, that is what we're looking after in the visible in UV, can be excited. So you can simply view that the electron is lifted. It goes into a different eigenstate. So that is coming from quantum mechanics, and you have then 1 vibrational and 2 rotational degrees of freedom. That can be explained even with simple mechanics, classical mechanics. You have an idea why? If you assume that the atoms, without any internal structures, would be just point masses, then each point mass given by God has 3 degrees of freedom. If you combine them, you have, for the molecule, 3 degrees of freedom, but you have combined 3 plus 3 is 6. And the number of degrees of freedom is preserved, which means 3 are left over. And then these 3 leftovers are going into 1 vibration. I think this is quite clear. These point masses can move only in this direction to each other, which we call a vibration, or they can rotate. And they can rotate only in 2 degrees of freedom, because if this is the molecular axis, you have this direction, you have this direction of movement, but you do not have that because you have point masses. Yeah? Then you have only these 2 degrees of freedom and rotation left over, which are degenerated, by the way. Okay, be careful. It could happen that in combustion, in chemical reactions, not always all of these degrees of freedom are in equilibrium. It might happen that you measure a rotational temperature based on Boltzmann, which is different than a vibrational temperature. It might happen. Yeah. Okay. Looking closer into these diatomic molecules, I show you here the internal energy of the degrees of freedom. The translational is left out. It's electronical states. Here are shown only the ground state and the first excited electronic state. And each of these electronic states, which are separated by a large amount of energy, we calculate that in wave numbers for historic reasons. We don't take joule or something like that. This is in spectroscopy in wave numbers. And the separation between here and here, for example, if you take NO, NO is of course an important diatomic molecule in combustion. The separation would be in wave numbers, maybe I'm wrong now, 30,000. Maybe someone knows better than I do. You need UV light to excite from the ground to the electronic state. It's a huge separation, yeah? Which means if you have 2000 Kelvin, the probability to find NO in this electronically excited state is almost zero, yeah? That is different for the other degrees of freedom. If you look for these different electronic states, they are split into different vibrational states. And the vibrational states here, only those values are allowed. Anything in between is not existent. And those vibrational states are separated by 1,000 to 4,000 wave numbers. For example, if you take hydrogen, then the separation would be 4,160 wave numbers, which is, of course, much less energy of the photon is required to excite that. Generally spoken, you need infrared radiation to excite a molecule from here to here to change the vibration state. And then, which is not feasible to show exactly in this view graph here, you have then, in addition, rotational substates, and they are, it's not working, here, and they are split as well in different rotational quantum numbers. They are called J levels. And they're the allowed states, how fast a molecule actually rotates. And that can be calculated with this formula taken out of spectroscopy textbooks, where you have here the vibrational quantum number, which is V. You have the rotational quantum number, J. And dependent on the molecules, these prefactors, that always contains the geometry, the masses, and the separation of the nuclei in the specific molecule. Yeah? And so the original reason to do spectroscopy was to measure this so-called term values, and then by measuring the energetic values of that, people were able to determine the values of these molecule-specific constants for vibration and rotation. And by that you can say spectroscopy originally was something like a measure, the possibility to measure angles in molecules, separation distance in molecules, bonding forces in molecules, all of that properties that are important to understand matter. We have that to a certain extent, with a certain accuracy, very often limited at high temperatures. However, with a certain accuracy, we do have these numbers and now can go backwards and use these knowledge about spectroscopy and measure concentration, temperature, velocity, and pressure. Okay, let's get even closer into how it's done. Referring back to Ludwig Boltzmann from Austria, you see here a view graph of him. For diatomic molecule, you can now, for the rotational substates, determine this or write down this distribution function. Now, this degeneracy factor is 2j plus 1. Without any proof, you have to believe me, that is this degeneracy for a given level Ej, which is a rotational state, and this is again the fractional population. And if you take, for example, a diatomic molecule, maybe CO or something like that, and calculate for 300 Kelvin how the fractional population over the different quantum states is distributed, you find something like that. If you would go to higher temperatures, all of these, this maximum would shift to higher values. Yeah? And behind that would be that the spectrum, each of these dots would be a spectral line in a rotation spectrum, would change if you have a different temperature. We will see that in an example later on. Of course, you can go as well and try to measure vibrational temperatures. Now, you see the Boltzmann equation for a diatomic molecule, and here the degeneracy factor is 1, because you have only this one vibration over there, and that's why it disappeared here, and now you have here the vibrational energies. However, as shown over here for the example of the nitrogen, different to the rotational levels, which were separated. I forgot to mention that. Separation between rotation levels in the order is in the order of a few wave numbers. 10 to 100. In vibrations, it's in the order, let's say, between 1,000 and 4,000. Nitrogen being somewhere in the middle, 2,300. What you see here is the vibrational band of nitrogen for temperatures from room temperature to 2,200 Kelvin. Okay? Each band consists of many rotation lines which are not resolved in the spectrum. Those lines are below this bands. But what you see is, if you go from 300 to 400 Kelvin, or if this is 400, then already the peak has declined, it's smaller, it has decreased, and it's getting broader. That means there are now more rotational lines underneath. That's why it's getting broader. And then something around 500 Kelvin, you see a second band shooting up. Yeah? This is now coming from the fact that, maybe I should show that in a graph like this. If you have here your separation between the two nuclei, you have here the energy, you have here the ground state, electronic ground state, and then you have here the vibration levels. Then this first peak over here, that is coming from the fact that you might have absorption from here to here, yeah, or population. You would make it visible by absorption, for example. But this would be the population in these lowest vibration level. The second peak here comes from the fact that if the temperature is high enough, you have starting population in the next higher level, yeah. Or if you go to even higher temperatures, here, then you see the second top band. That will be population in this next level in the vibration. And by that you see the spectrum in absorption, for example, is strongly changing with temperature. Yeah? But below 500 Kelvin, you can say it's not very sensitive. Yeah? Because the vibrational temperature would be the ratio between this hot band and the ground band, or the lowest band. And that shoots up only for sufficient high temperatures. So measuring the temperature vibrationally means you can do it not for room temperature very easily. Impossible it is to use the distribution in the electronic states. I have shown that now for the electronic states here, the energy is now in the order of a couple of 10,000 wave numbers. And that means at combustion temperatures, there's no significant population of electronically excited states, and thereby you cannot exploit that easily, except of some atomic traces that people have used, like indium, which is not detailed in this lecture. So that means the best way to measure temperatures is via the Boltzmann distribution of the rotational sublevels. And now the question is, how do you do that? How do you probe the distribution of the rotational sublevels? Well, I refer here for the moment for single photon resonant processes, meaning that you want to try, for example, by absorption, to see how strongly is the population in this state from which you start the absorption. And for that you need resonantly tuned laser light, or not laser light, excitation light. Yeah, you need a photon. Its energy can be calculated based on its frequency and the Planck's constant. And if this energy is matching this energy difference, then you have a certain probability for absorption. If you have that, well, you could think of directly measure the rotation spectrum in the rotational subbands. But you would need something like light in the order of this energy separation being in the microwave region. So in principle, you can think of doing that, but do you have any idea why this is not very, very good in combustion applications? Microwave radiation means you have waves with wavelengths in the order of many, many, many centimeters. And that means you have no chance to receive a good spatial resolution. Yeah? In addition, you have to guide these microwaves in waveguides, and so that's not very feasible to be, or applicable to flames. And so that's why rotational spectroscopy, it's a very powerful tool in general, but it's not very good for combustion diagnostics. So let's have a look whether we can do it differently. We switch now to rotational vibrational spectroscopy. Now, we not only change the rotational level, but simultaneously we change as well the vibrational sublevel. And that means we have here energy separations between, as I said, 1,000 to 4,000 wave numbers depending on the molecule. That means we're in the infrared region. I show you an example of HCl. That is as well for coal combustion, for example, very important as a corrosive material. If you do absorption spectroscopy as a very easy technique, you shine in the laser from the left with the intensity I0, and then after a path length of L, you have only left over intensity of I. And then with the simple Lambert-Beer law, you can deduce the number density, path integrated number density, independence of the measurand, the measured intensity after the cell, before the cell, X is the path length, and sigma here, that is the absorption cross-section, the probability that a photon is absorbed. And if you now tune your infrared source in this wavelength or wave number region around 2,900 wave numbers where HCl absorbs, you see then very nicely an absorption spectrum like this. Yeah, you have two branches. One is called the P branch and the other is the R branch. I discussed that in detail what's behind that. And you nicely see as well there's a gap in between. This is a so-called zero gap. And what you see, and this is now the important message, you see that these lines have a certain shape. And this shape is just a function of temperature. If you draw an envelope, for example, like this envelope is a function of temperature and would change if you go to a different temperature. Yeah? And so the temperature is coded in the relative intensities of these absorption lines. And that is the basic idea. The best thing is, of course, is you measure the whole spectrum. That might be a problem. If you have turbulent combustion, you must finish your measurement within, let's say, a microsecond. Yeah? And measuring a full spectrum within a microsecond would mean, in absorption spectroscopy, if you do it one wavelength or one wave number after the other, you have to scan your laser extremely fast. Yeah? To go from here to here. In principle, that's feasible. With diode lasers, you can do that. Voxel lasers, for example, can be tuned within a microsecond. Maybe not the full band here, but maybe only a small range of 30 wave numbers. A voxel laser with 1 megahertz tuning velocity is maybe feasible only to scan over 2 of them. Yeah? And then you would have only the ratio of 2 these lines that can be then used for determining the temperature. But before going more into this thermometry, you should be aware of some more findings from quantum mechanics. I think that is very important to be aware of. The first is that you cannot, if you have a certain state from which you start, and you have absorption, you cannot end in an arbitrary state. You have so-called selection rules. For the vibration number, actually, there are not really selection rules. The vibration number can be changed plus minus 1, plus minus 2, whatever. Here, in the rotational quantum states, that is quite different. There, only a change of plus minus 1 with a few exceptions is allowed. So plus minus 1 in infrared spectroscopy is the norm. That means if you do have, here is shown the lower part, is the initial vibration level. We call that with this, how you call this? Double prime. And you have here the final state, V prime. And well, the energetic separation from here to here is in the order of HCl, 2,900 wave numbers. So this is that's why it's dashed over here. But magnified are the rotational sublevels in the ground state and the first vibration excited state. And the selection rules mean that if you have, for example, delta J plus 1, then you are allowed only in spectroscopy to change the quantum number. Take 5 as an example. This is going up to 6. This would be the so-called R5 line. Or the R7 line would start from here and would go to J prime 8. The P lines linked to -1, they go, if we refer back to the P5 line that is here, that goes to the J level in the upper state number 4. Yeah? And by that, this spectrum of HCl that you have seen here is so well sorted. Yeah? You have here the P lines, delta J -1, and the R lines, delta J +1. And the Q lines that would be have delta J equals 0, that are not allowed. So you don't see any Q branch here. And by that, well, for diatomic molecules, it's rather simple, and the spectrum are well behaved and consist now of this R and P lines, and with exceptions as well, sometimes the Q lines. Well, you can learn, of course, more from this spectrum, and that is shown here. First, the line dependency, the temperature I just mentioned. But what you see as well, there is no Q line, and what you see as well, and that's maybe what I should stress a bit more, you see here that it's not a single line, but you see these doublets. And those doublets come from the fact that you have chlorine with a different number of neutrons. And so they have different weights. And that traces back to this rotational constant. Maybe I should go back, it takes a while. This rotational constant is in this equation here. This is called B, and for the corrections, D. Here is the mass going in of the molecule. And you have a different mass, you have a different rotational energy. And this gives rise to the fact that you have close lines which are close to each other, but are clearly separated. And by that, I can directly measure the occurrence of 37 and 35 chlorine that is abundant in nature. Okay, of course you can not only do it with infrared spectroscopy, but you can probe the rotation temperatures as well with electronic spectroscopy, measuring in the UV or visible, where the energy separation is now in the order of more than 10,000 wave numbers. And there you have even more selection rules. It is not only for the J number, where now the Q lines are allowed. Delta J equals 0 is typically allowed in electronic transitions. You have the Frank constant principle for the vibrational transitions, but you do have as well a number of additional selection rules for the electronic states. And maybe this is going too far now, but you have here a selection only. For example, delta S equals 0 means that the spin of the electrons in the ground and excited states are not allowed to change in this transition. Yeah, and that is, for example, a spin forbidden transition would be a singular triplet transition. And when I mean forbidden, that means it's not very probable. It doesn't mean it doesn't happen. Yeah, and I stress this here, especially this triplet singular transition. In phosphorescence, we exploit that, which means that it takes quite some time to appear, but it does exist. And so the intensities are lower, but we can exploit it. All right, and if you now look into a schematic of the electronic spectrum, you see here this electronic ground state, electronic excited state. You see the different vibration levels. You do not see the rotation levels. That would be each of these vibration would be subdivided in its rotation levels. And now presume that we have, for example, a laser absorbing from or kicking the population from here to here. Then you have not only P and R lines, but as well Q lines. And then your spectrum would look like that. That, for example, the R band with the different quantum numbers. The quantum number is going from 0 to only limited here to 25. Of course, it goes to infinity. Then the corresponding electronic states, or the eigenstates with the wave numbers, are listed here in this x-axis. And here are the corresponding lines to the R0 line, R1 line. They would be placed over here. And in electronic spectra, you typically find an R bandhead. So for increasing wave numbers, it turns over, whereas the P and the Q branches are continuously going into one direction. Yeah, and so those lines, the P and Q lines and the R lines, which would overlap to each other, and you would find, especially in this region, rather complicated spectrum giving or arising from this different branches, from the P, Q, and R branch. Okay? And here's an example of OH. You have historical reasons for absorption to have an arrow going from right to left. That means this is the electronics ground state from which absorption happens, and this is the electronic excited state to which you absorb. And right of that you see the transition in terms of vibration, and then you see here a part of the spectrum only of the R bandhead, where you see here different lines. I've marked only the R18 line of the spectrum, and I've shown that here for 18 bar at relatively high pressure and different temperatures. And as you see, if you change the temperature, this absorption spectrum is changing. Maybe we take the black line, 1400, and the blue line, 2600 Kelvin. And maybe take this absorption line over here at 2600. This is much lower than at 1400, simply because of the Boltzmann distribution. Yeah? And so if you would probe such a transition over here and relate it, for example, relative to that one, which is much less temperature sensitive, where the variation between 1400 and 2600 is only this compared to this, of course the ratio will be a unique function of temperature. And that is how you can exploit it. You have questions to that? Or is the basic principle okay? Yeah?
Maintain that temperature, 1400
This is a pure simulation.
simulation.
This is a pure simulation. Yeah? Purely calculated here. 2600 would be not so easy. With oxy-fuel combustion you would be able to do it. Oh, it's back to life, maybe. Well, we have now different options how to probe these rotational sublevels. You can use absorption spectroscopy, I mentioned that already. You can use laser-induced fluorescence. In principle, you can use Raman spectroscopy, coherent isotope spectroscopy, and these are the options we previously discussed. So let's get started with absorption. You already see this graph where you have the line of sight method. You have low resolution in direction of the laser, and of course, perpendicular to the laser, that will be a high resolution in space. Now we are back. Thank you. And you've seen already this Lambert-Beer's law. This is the original form where you see that the intensity after the transit is changed by this exponential term, where the number density goes in. The more absorber you have, the less the intensity at the exit would be. And the path length, of course, goes in as well. The longer the absorption is, the more the smaller the measured intensity at the exit is. But this presumes, and that is the drawback of this method, that along the laser path, everything is homogeneous. If you want to measure a temperature, then you have to be sure that the temperature is constant along this line path. And for that reason, this method is not so well suited, for example, close to a nozzle of a burner, where you have a huge variation of temperature. But if you're in the exhaust pipe, for example, then this is a very powerful technique. The most simple way to determine now a temperature based on Boltzmann's distribution is you would take a measurement at two lines and measure the fractional population of two rotational sublevels. So those are directly coming from this equation. So you know the length, you know the absorption cross-section of each transition, you have the initial intensity, and you measure the final intensity with this detector. So you have this number, and you put this into the Boltzmann distribution for these two measurements. You know the energy separation between the two sublevels, and you can resolve for the temperature. And the nice thing here is, if you have looked at this carefully, the partition function has disappeared, it cancelled out, and the absolute number of molecules per probe volume have cancelled out as well. And so by that, because you take the ratio, you get rid of these unknowns, and you have a so-called two-line thermometry. If you have a two-line thermometry, do you have any idea why it is maybe not really precise if you do it in a short measurement time? Say it again. The temperature, let's say you have a constant temperature, and you measure it at a small, still at a very short time. The problem is if you have any noise, yeah, and take two noisy measurements and take the ratio of that, which means this is something like a slope, so you have a huge error. And so maybe we can switch that on again. You have maybe if this is the true value, because of noise you have that, and then you, depending on the instantaneous realization, you might get a slope like that, you might get a slope like that, and that is a function of temperature, and so this is heavily disturbed by noise. Yeah? And so to make a two-line thermometry really reliable, you have to have a measurement with really minimized noise on your measurements. Yeah? It is much better if you measure the whole spectrum. And that is the primary benefit of cars. You will see later on in cars, you really measure the full spectrum and thereby have much higher precision. However, you can do that, for example, as shown here, where you now try to spectrally, if you have a spectrum like this that has been taken with a diode laser, I think in absorption with a near-infrared vibration spectroscopy, and where you see the other method, instead of having here a ratio, you try to fit a theoretical spectrum to the measured spectrum, and now you might have multiple lines in this spectral region, and you fit by the temperature. The temperature is the only variable after you know the line broadening and so on. Then you can determine that as well from a fit. So very good is about the absorption technique. It's very sensitive. It is accurate because you trace back to the Boltzmann distribution, so there's no calibration required. And if you want to achieve a high accuracy, really, you need a multi-line thermometry, and if you want to be precise, you need a very low noise detection device. However, you have only a high spatial resolution perpendicular to the laser. If this is the laser in this direction, it's good. Along the path, it is not existing. You have no resolution. And so that is the primary disadvantage. It is a line of sight technique, yeah? Because you don't have any resolution along the laser. The other is when you want to have a multi-line thermometry, you need a really fast laser to tune, because you have to tune it across the absorption lines. And that can be done with diode lasers, but that cannot be easily done, for example, with a dye laser. Yeah? So you're strongly restricted to a few laser sources unless you have multiple lasers. Yeah? If you, for example, want to do a three-line thermometry based on a UV absorption, where you don't have a diode laser that you can tune, you would have to use 3 UV lasers. And that would be very costly, and no one would do it. Yeah? Okay, so in general, you can say it is really great in laminar flames, where you have, let's say, in the direction of the beam, no spatial variation. For example, the Wolford-Parker burner, which is a slot burner, yeah, where you have a translational symmetry along the slots, there it is a really great thing. Or the Suchi burner, you know the Suchi burner, some of you? That is a counterflow burner where you have, for example, methane coming out from the top from a porous plate which is curved, and a wind tunnel. From the below you have air, and then you have a 1D flame in the stagnation, across the stagnation point, and you have a translation symmetry in one axis. And thereby you can apply absorption spectroscopy very nicely. But if you want to have a better resolution, you'd have to do it differently. Otherwise you could stop. And that is laser-induced fluorescence. And for those of you who are not familiar to that concept, you first have absorption that is done here, like an absorption spectroscopy. But the difference is now, you look later on, what is the fate of this electronic excited state? And here typically it must be electronic excited. Otherwise, if you vibrational excite it and wait for infrared fluorescence, that takes far too long. And the excited state would be heavily disturbed. In electronically excited states, they are not very long living, such that you have a high probability that the system crosses over into a lower state and thereby emits radiation, what we call fluorescence. And in this case, we have had first an internal relaxation and then fluorescence back to the electronic state, but it doesn't need to be in this scheme. It can be as well first fluorescence and then relaxation, so all of that would happen. And so this is now what we measure, and typically that is redshifted. Not always, but in most cases, the wavelength of the absorption is smaller than the wavelength of the emission, and that is something we call redshifted. It is going to higher wavelengths or smaller frequencies. Yeah, well, if you look now into the equation describing linear laser-induced fluorescence, or shortly LIF, then you find that your measured intensity depends linearly on the number density of your probed initial state. And that is what we're after. That is great. Now, what comes in addition to that, it's a bit more complicated than in the Lambert-Beer law for absorption. You do have a number of additional terms. Some of them are not so problematic. Some of them are actually desired. The probe volume, for example, we come to the detection scheme in a second, that needs to be calibrated somehow. That should be very small to resolve the small scales. You have a certain angle in which you detect. Yeah, 4p would be fluorescence takes place in all directions. If you excite something, then it's electronically excited, and then it takes maybe 1 to 2 nanoseconds before it fluoresces, and the fluorescence, in a good estimation, is isotropic. And so if you now have a certain lens, you just capture a fraction of this, which is expressed by this term. Then your optics might not be perfect, and you might have some transmission losses, epsilon. Then your detector does have a certain quantum efficiency, and maybe not every photon from fluorescence is detected. And that can be quite bad. It might be only 10% of the photons that come are actually detected. Then you have the laser intensity, which is convoluted with the line of your absorption. So that is typically known. This convolution can be taken. Laser intensity is measured. Absorption cross-section we know as well. And then we come to the problem. The problem is actually this total lifetime. So if you have this excited state over here, then it takes a certain time until fluorescence takes place. Yeah? And although it's only a few nanoseconds, in this time there will be collisions with other molecules. And if you have that, due to these collisions, the energy is taken away. We call it quenching. It's quenched. And the colliding species has taken over this energy. This colliding species is now faster, or does have a higher internal energy. However, the energy of the fluorescing molecule is gone, and it will not fluoresce anymore. And now, this total lifetime, and that is the problem, depends on various parameters. And the total lifetime depends on the temperature, the pressure, and the species. Yeah? If you change the gas matrix around it, the total lifetime will be different. And so as you see, you have only one measurand, and the unknown quantities is n and the total lifetime. And so two unknowns and only one signal, this of course causes problems. And so it will go too deeply. If you want to exploit that really to measure concentrations, then you have a problem with this. Yeah? You can solve that. However, I will go to thermometry, and then under certain assumptions you will see it will cancel out. However, before we come to that, you should have an idea about the principal setup. You shine in a laser, maybe focused, and then the difference to absorption is that you measure typically perpendicular to the main beam propagation. Perpendicular to that, you measure your fluorescence. And thereby, you cut out, although all the way you will have fluorescence, by focusing this spot onto your detector, you will looking only at that spot. And you can do that pointwise along a line. You can do that in 2D if you have a array detector. Typically, you have here in addition as well a filter. Why that? Because your fluorescence typically is redshifted to the absorption, and you want to get rid of any reflections or any spurious scattered light from the laser into the detector, because that would be maybe too strong. If you, for example, have seeding particles from PIV, the laser would be scattered into the camera, and that would be superimposed to your fluorescence signal, and that would not work. And that's why you typically filter out any radiation from the laser. And here's now an animation how it works. That is a simple Bunsen flame. So the nozzle would be here. It is slightly rich, and it is laminar, but it's not stationary, just to exemplify it. That is in the transition deep in the UV of the OH radical at 248. You have an electronic transition from the X to the A state, but you go into the third vibration level of this OH, and you see to the left-hand side actually the laser, the red line, that is the laser. And when I tune the laser, now it's moving. We are not at any transition, and still you see fluorescence. So this is a light sheet going like this through the flame, and perpendicular to that, we look with the camera on it. And this is fluorescence from C2 radicals. It's a rich flame, and that's why C2 radicals at this inner erection layer is present, and you see you can excite that. However, this is color-coded. Intensity is high when it's getting red, and black is no fluorescence. And now I stop the laser. Now we see fluorescence from all over the place where we have OH, and that is actually here in this layer where you have this rich flame. Then you have dilution with air, and you have as well a second reaction front somewhere here, and in between you have hot gases. And now I stop it again. Now we are on resonance. And now for a simple visualization, you would do the following. You would park your laser at this transition, for example, and now you would see where you have OH. And now you as well see the problem with this kind of lasers. You see here areas with reduced fluorescence intensity. That's unphysical. Yeah? That is simply because those excimer lasers, that's how they're built, they have a non-homogeneous intensity distribution. So the intensity profile has a hole in its middle. And because of this lower intensity in the middle, you have less excitation. These are raw data. So what you have to do, minimum, is to normalize at the laser intensity. And that already is not so easy. You can do that maybe beforehand. You take the laser intensity profile, averaged over 1,000 shots, and then you average or normalize this distribution on your averaged intensity profile. What do you do if your laser is not constant? Yeah, very often laser intensities are not constant from shot to shot, and they change. And then you have to do it shot-wise, and that is a more complicated experiment. However, what you see as well, this was detected with an intensified CCD. An intensifier always add noise. If you look carefully here, for example, are regions where you have high intensity, low, high, in a small range of a laminar flame. That cannot be true. Yeah? So this is overlaid by significant intensifier noise. And so whenever you want to measure anything quantitative with an intensifier, you're generally spoken in trouble, yeah, because of the noise issue. Yeah? The best is you can somehow avoid to use that intensifier. Okay? I think the rest is clear. We don't have to wait for all the spectrum. If we go again off resonant, still the OH is gone, but the C2 stays. And that is another problem in spectroscopy. Very often you have what we call interferences, not in the sense of diffraction, but in the sense of that you have excitation and fluorescence in the same area, in the same spectral area. Okay? Okay. Let's have a look how we can use now fluorescence despite of its limitations for thermometry. You can do it again by probing two lines. Yeah, excite two different transitions such that in the signal intensity depends on the fractional populations, and therefore you can trace it back with the Boltzmann distribution to determine the temperature. Well, however, you should be a bit careful, but this holds true for every kind of two-line thermometry. On the temperature range you're interested in, none of these number densities should be too small, because then you have a small signal for a given noise, that would be as well limit your precision. However, if you now use that equation for these two quantum states you're probing, you can calculate a ratio, and what you see is there are calibration constants going in, depending on the detection of angle, depending on the detection efficiency, and so on. You have the laser intensities going in. You have, from quantum mechanics, these degeneracy factors, the corresponding energy eigenstates. And then you have here as well the total lifetimes. You have the absorption cross-sections, you have the how well the laser is convoluting with the absorption line, all of that is shown here as well. But still, you have the effective lifetimes. And now it depends. If you have a molecule where the effective or total lifetime is more or less independent of the rotational substate you excite, then they cancel. Then you're fine. So very often this is the case, and you can say that these are independent of the rotational sublevels you have probed, and they cancel, but generally that's not true. If you have a molecule where you have a strong dependency, you cannot do it, and then you stick with the problem that you have to know about the effective lifetimes. Yeah? And if you have to know about them, you have to measure the effective lifetimes for these conditions beforehand. And how would you measure a lifetime of a quantum state? Have you any idea? How do you do that? Maybe I show it to you. In principle, the principle is easy. The realization is difficult. You measure the fluorescence over time after a very short excitation. For example, take a picosecond laser such that you initialize your upper state population at an instant of time, which is much shorter than the lifetime. And then you just wait and measure the fluorescence, and maybe you just take the logarithm of that, and you have very often a mono exponential decay, and then you have something like that. And this is a function of the effective lifetime. And now you change the temperature, you change the gas composition, and you will find different slopes. And from that, you can deduce the lifetimes. Okay? But here, if you want to put that in, you have to know beforehand, at least in a certain range, the gas composition, pressure, anyhow, and the temperature. And now you see what the problem is. Yeah? So those are temperature dependent. And you would be lost if those would be strongly temperature dependent. And so very often the ratio of these effective lifetimes is not so strongly dependent on temperature, such that you can say it's almost independent, and then you can say that this ratio here is a unique, not a unique, but it can be directly linked to the temperature itself. Yeah, but you see, this effective lifetimes even here in the temperature measurement can cause a problem, although it's very often ignored, and people just cancel it out without saying anything about it. Yeah, but it's not true. Better is to make multi-line thermometry for the same reasons as for absorption, that you have the potential for higher precision, where you, for example, measure the entire spectrum and then make a fit to it. Or the method number 2 is, if you have measured these multiple lines, you take the ln of the signal intensity, plot it over the ground state, and then you get a slope which is a unique function of temperature. So this is these two methods you can perform. However, again, they're applicable only in laminar flames because it takes quite some time for the wavelength scan. Yeah, so that's not applicable for turbulent flames. However, but the two-line thermometry in principle is. But of course, if you do it in a turbulent flame, for the two-line thermometry, you have to take 2 lasers, 2 cameras, and still have the problem with the effective lifetime. What are the molecules you can take? For example, you might take molecules that occur naturally in your flame, like OH radicals, but then you're restricted to temperature regions above 1500 Kelvin roughly, because below there would be not very much OH for fluorescence left over. You can seed species into that system, such as NO, that is regularly done. This is more or less inert, but you need maybe 1 ppm NO is not sufficient. Maybe you need a minimum of, let's say, 100, 200 ppm or so. if you're interested in autoignition, be careful, because NO might influence autoignition. And here we have something again. This is not non-intrusive. Yeah? You add something to it, chemistry might be changed, and you might be in a problem. People have done as well, or used traces like indium that is introduced, for example, in IC engines, and by dissolving indium chloride in the isooctane, for example, and then you bring this indium is then produced in the flame front, and then you can probe here two states, which is as well used for thermometry. Okay, the third possibility to look for quantum states and the Boltzmann distribution is use Raman spectroscopy. Raman spectroscopy is a totally different process, but maybe I should make a short rest and give you the opportunity for any questions according to LIF.
In that scan with excimer laser,
Yes.
where OH and C2 was,
Yes.
what was the filter?
The filter was actually, it was an excitation at 248, and we were looking for the fluorescence, I think around 290, 300 nanometers, something around that. And this was a filter, by that early times, we have used a reflection filter. If here is the fluorescence coming, this was a set of 4 mirrors arranged in such a way that the radiation came here. And this was highly reflecting mirrors only for wavelengths, I think above something like 260 or 270 nanometers, I don't remember exactly. And 248 was hardly reflected, it was transmitted. And because this was black here and here and here, such that there was no leakage, the transmitted 248 was, by this action of the 4 mirrors, more or less removed. Nowadays, I would do it differently. You just take a single dichroic filter and getting rid of the 248 and transmit anything above 260, for example. Yeah, you have specialized companies providing those filters. They can be very effective, but if you have a special wavelength option, it might be as well quite expensive. Yeah.
It's a long pass.
That's a long pass filter. And typically then, if you have, let's say, remaining light from the lab or something, you have a UV transmittance and you block anything, again, above, with the second filter, above, let's say, 350 nanometers or so. Yeah? It could be as well something like a UG11 filter, which is quite cheap, or UG5 filter from the company of Schott. You get them, and they do a fairly good job.
Yeah.
Yes?
Do you have any results that you have obtained the temperature for the laminar plate? Do you have any results?
Yes. We haven't done that because I'm not measuring laminar flames, but for example, what comes up to my mind, people in Duisburg, Christoph Schulz, for example, they have measured temperatures by NO. They have added NO to the laminar flame, and then they have made a scan in the UV, and from that scan they fitted a spectrum to it, and from that obtained a temperature. Yes, I can look for references for you, but that has been done. Yes. Yes.
Is it a linear?
Pardon me?
Is it a linear variation?
That is a linear dependency, as long as you have, maybe go back here. As you see, the exponent here is 1. Yeah, so this means this is in the linear regime of fluorescence. That means you have to stay with your laser intensity below the so-called saturation intensity, which depends as well on the quenching, by the way. Yeah, but that should be tested, that you're in the linear regime, and that can be tested simply if you change the laser intensity by a factor of 2. However you do that, you should have as well then a change in the fluorescence signal intensity accordingly by a factor of 2. Yeah, it's here non-saturated LIF. Yes, please.
You have assumed here that the quantum state, like, it is a diatomic molecule.
Yes.
What if in the composition there is a triatomic molecule and you cannot put any diatomic molecule? Then how can you use this technique to measure temperature? Because then those quantum equations will be different.
Yeah. Well,
the vibrational states will be different.
that's absolutely true. Spectroscopy is getting nonlinear more complicated if you increase the number of atoms. And so you will see possibilities how we do that by traces like acetone or toluene, or so I think my example would be toluene. There, we do not resolve all the spectroscopy because as well, we cannot see single or separated rotation lines. Everything is so dense that we just see the bands. And then we will see how bands, either in absorption or emission, change due to temperature. And so we don't refer really back to Boltzmann distribution. As well, as I said, we can't resolve all the lines, but look for these more global features. And then with the calibration, we can trace back these changes in the spectrum to a temperature. But that comes, and these are really for more than 3 atomic molecules, toluene or 3-pentanone or whatever they are. They are large molecules. You will see the formulas maybe tomorrow. And then it can be still used, but it's not calibration free anymore. Okay? Yes? How we calibrate. One way to calibrate, the typical way we use for calibration is to use well-known laminar flames. Yeah? For example, like a Bunsen flame, if you have something like you want to measure at 2000 Kelvin or something, you cannot use a calibration source like heated gases. You wouldn't obtain that. You cannot use thermocouples, as explained. So you use a flame where you know its behavior. Yeah. Ideally, you have checked that the laminar flame behaves as you wish, for example, by using coherent anti-Stokes Raman spectroscopy, really to make sure that you have an adiabatic flame. Yeah. But that can be done then if you have this calibration flame that you know exactly at this location is this or that temperature, that you really refer back to that. And because if you have these calibration constants here in the two-line thermometry, those have to be somehow taken care of. And that is because C1 and C2 might be different. If you have, let's say, two detectors and you have different lens systems or so on, that might be a problem. And then you have to go back to the calibration source, as I said, that can be a laminar, well-behaved, known flame. Okay? Yes?
So this might also change if I calibrate in a very simple flame and then use it for a very complex geometry where the wedge or whatever tracer we are tracking. So the species density will be very high.
Yeah, it can change. If you have a high species concentration, for example, it might happen that your fluorescence is reabsorbed. We call it radiation trapping. And then if the radiation trapping is different for these two, let's say, branches, depends on where the fluorescence is, then it might cause problems. That is correct. Generally spoken, whenever you change your setup in this ratio method, you have to recalibrate. You need to make the calibration really with the same optical elements. If you have, for example, a high-pressure combustor or whatever, then you should do the calibration with having inside the combustor your calibration source, that you go through all the windows. Because I think if I have time tomorrow, I will exemplify that for thermographic phosphor imaging, where as well people use the ratio method. Whenever you change suddenly a very small amount of angle or something like that, you can end up with a different calibration. And for that reason, in situ calibration is very, very important for this ratio method, to my belief. Yeah.
If you are calibrating with your premixed flame, how this particular calibration data can be used for your non-premixed flame? You are trying to extend that.
You can't use it if you're really correct about it. You can't use it. Then you might use a different calibration, something like opposed jet flame or whatever, and then it gets impractical, right? Because then maybe you need a translation stage with two burners on it. Yeah, it's getting very fast, quite complicated to make a good calibration here. Yeah, and so that is maybe as well why you don't see so often temperature measurements via LIF. Yeah, cars is here much more robust. Other questions? All right, then let's at least. I have 15 minutes left. Is that right? Yeah. Let's get started with a completely different kind of spectroscopy. What we have heard beforehand was based on absorption, allowed transitions, where you have tuned your laser resonantly to a transition to get from one initial to a final state. Now, in Rayleigh and Raman spectroscopy, you have excitation radiation, which is not resonant with any allowed transition. You just shine in a laser, and this is shown schematically in this axis. There's the energy. This is the energy of your exciting photon. As you see, here is no allowed eigenstate, and that means the molecule cannot exist at this energy level. It will leave that energy level directly and go back, for example, to this initial state. And then what you see is what we call Rayleigh scattering. What you do is, and maybe tomorrow I explain in more detail, you drive by the laser excitation a polarization. What you do is, if you assume you have a molecule consisting of a nuclei, positive charged, and negatively charged electrons, what you do is, by the electrical field, you bring them into an oscillation, okay? And this is like a dipole, an oscillating dipole, and if you put that into Maxwell equations as a source term, you can show that from this dipole you have radiation emitted, not isotropically, they are preferred directions. However, in some directions you find here what we then call the scattering process. But this is not a scattering process like in particles, yeah? It's completely different. Yeah? It's not off surfaces, but it's due to the action of a polarization. And if it returns to its initial state, you find here the Rayleigh scattering. This is proportional to the density. Yeah? We will see that Rayleigh scattering via density can be used with the equation of state to determine the temperature. But here we are still with the Boltzmann distribution. That's why we go to the Raman process. In the Raman process, you have, in the sense of a mechanical sense, an inelastic scattering, because after this process, the molecule stays in a higher or in a lower energetic level. If this takes place, in this case, then you transfer some of the energy to, for example, rho vibrational energy, and your scattered light, your Raman scattered light, is redshifted. It has a longer wavelength, a smaller frequency than the initial exciting radiation. And this is called the Stokes shift. But it can happen as well, the so-called anti-Stokes shift. If you start from a higher level, the scattering process, you end up in a lower level, then your scattered radiation does have a larger frequency or a smaller wavelength, and it's blue shifted, and that is called anti-Stokes. However, with either Stokes or anti-Stokes Raman spectroscopy, you can probe as well the number density for the Boltzmann distribution. And here you see, on the one hand, on the left-hand side, the selection rules for Raman. They are different than for absorption. You see that plus minus 1 is not allowed. The P and R branch do not exist in Raman, or only if they exist very, very, very weakly, like in O2. There are very weak lines. They can't be really seen here. Much stronger are the S and the O branch, and of course the Q branch, which is the strongest over here. And again, what you see here is an ideal spectrum, what we call a stick spectrum. Only the line centers are drawn for a certain temperature, 1500 Kelvin for oxygen. If you would change the temperature, then this distribution would be completely different, right? And again, the shape of the distribution is decoding the temperature. In the experimental setup, it looks very similar to LIF. In terms of the spatial resolution, it's exactly the same, that the radiation typically is taken perpendicularly to the laser exciting direction. But in addition, you need a spectrometer, because now you want to resolve, depending on the resolution, what you're after. That might be a meter spectrometer or a smaller spectrometer. We come to that later on. You somehow have to disperse now these different frequencies, because in difference to LIF, where you have excited only one line, you now excite the whole spectrum, because from each state which is populated, you find this scattered light, okay? You have only one laser, but all the transitions directly included. And so you need then, at the detection site, something to distinguish between these different population levels to get the fraction population. And here you see something which is not directly referred to thermometry, but is more for concentration measurements. If you have a spectrometer, which is now consisting, it's not very highly dispersive, you see as well the impact, this is just a side note, the impact or the spectrum of different species. And maybe that is something important to understand as well. This is as well a beauty of Raman. Maybe we can show that here in a next slide. If you presume you have two different molecules, and I make it as easy as possible, only draw two quantum states. This is molecule A and this is molecule B. And then you shine in one and the same laser. They have the same energy. Then you have Stokes scattered radiation. This would be lambda Stokes of A, lambda Stokes of molecule B, and those would be different. Oops, this must be B Stokes. They are different because the energy separation of the initial and the final state is different. And because this difference, the scattered light must be different as well. And if you disperse that in the spectrometer, then you can distinguish after 532 nanometer excitation, for example, the N2 peak in the exhaust of a non-premixed flame, or in the reaction zone it is actually, where you see CH4, water, hydrogen, CO, O2, CO2. Yeah? If you do that properly, you can determine from such a spectrum not only the temperature, but as well the species composition. Yeah? That is a very, very powerful tool. The big problem with this is that the Raman cross-section is extremely low. If you have a low dense fluid, like a hot flame atmospheric, you need a huge number of photons that you create a few Raman photons to be collected. And that is a very, very, very bad signal, a small signal, and the problem is then always the signal to noise. You must have a very, very low noise detection unit and many photons to excite to make that happen. And that is why this is maybe one of the most useful techniques we have in combustion diagnostics. But because of its difficulty, there are only less than a handful labs in the world doing that. Yeah, because although by principle it's very easy, in practice the signal to noise is a problem. And now maybe another point that has to be stressed out very clearly. The big benefit in this scheme is that the lifetime of this state here, which we call a virtual state, doesn't exist. It's not allowed to be there. This lifetime is, I don't know how long, maybe 10 to the minus 19 seconds. Extremely short, much shorter than any collision rate. Yeah? Such that any collisions here do not interfere. So there is no collision quenching. And that means you can directly relate your Raman signal to a number density. Yeah? And that is, there is no effective lifetime or anything. And that is the big benefit, that you directly can quantify after calibration. You can quantify the Raman signal and get a direct measure not only of concentration but as well on species. Okay. However, coming back to thermometry after this side note, what you can do, for example, is you measure the ratio of Stokes to anti-Stokes intensities. Yeah? You do this process simultaneously with that one from an excited level, and you refer to the fact that you have a direct proportionality, and if you have, let's say, the same quantum efficiency of these two radiations, which might not be true, yeah? Your detector might be different sensitive for the different wavelengths. You have to account for that. This is now already taken out. If you have calibrated for that, then you can take the ratio and again come to that formula, make it two-line thermometry, which is based, for example, here on two vibration levels, which is typically done if for vibration levels, but then you can do that only from, if you, for example, take N2, you can do that only for temperatures above 500 Kelvin, because otherwise the fractional population of this level would be almost zero. However, that is not very popular in the combustion community. I don't know really why, but because for some applications it might be a good choice. If you, for example, go to a gas turbine combustor where you have preheated air anyhow, above 500 Kelvin, it might be a choice. Another possibility is to measure the entire spectrum, as shown here. And now we refer only to the Stokes sites, forget the anti-Stokes, and come back to that image again. You have seen that, where you have a high resolution in the order where you resolve. Now, these are 100 wave numbers. You already need a highly resolving power in your spectrometer to distinguish the shape of these bands. You're not able to resolve the single lines, okay? That would be very, very difficult. However, if you don't have this spectral power, you still could be taking these envelopes from these bands, and you directly see from these envelopes that is as well very temperature sensitive and could be either calibrated, or you can as well calculate a spectrum of N2 and try to fit it by changing the temperature if you have the line width of your spectrometer. That's as well not very common in combustion research. Why? The signal, if you send it through a 1 meter spectrometer, the transmission efficiency is very low. And so your signal to noise would be rather bad. Yeah? In single shot, if you have just a single laser shot to create such a spectrum, you might stuck in a too low signal to noise, and you can't do it. If you have time to average, like in laminar flames, that might be feasible. Okay. With that, maybe I make a cut over here before we go to the real interesting thing, which is then coherent anti-Stokes Raman spectroscopy, is the only nonlinear technique I'm going to explain then tomorrow. But maybe there's still some time for questions you might have. Okay.
We use this LIF technique to measure the temperature variation inside internal combustion.
Yes, that can be used. I have tomorrow examples based on toluene LIF, which is based on a seeded species, where we have used it, but only in the unburned part of the engine. It is feasible, yes. With these kind of traces, it's only possible in unburned regions, because in the flame front, these traces would be consumed. Okay? You can measure crank angle resolved. Yes, I will show it tomorrow. Okay? All right then. Thank you very much for your attention, and have a nice lunch.